Hello and good day everyone. My name is Nur Zakira binti Zainuddin and I'm a final year student from Faculty of Engineering University Putra Malaysia under the Department of Computer and Communication System Engineering. In this video, I'm going to present my project titled Genetic Algorithm Pretrained Model for Deep Learning Architecture based on FPGA. The project was proposed due to several problems that have been identified. So firstly, the problem is due to the limitation in terms of throughput in conventional neural network implementation platform. So as we know, due to advances in technologies, the amount of data available nowadays also keep increasing. So to handle all those data, the interest of people toward artificial intelligence, especially in the area of deep learning, are increasing. But it is also important for us to take note that while the usage of deep learning model have huge advantages in various recognition fields, deep learning had faced its computational limit in the current platform it was being implemented, such as CPU and GPU. So because of this issue, FPGA had then emerged as one of the platforms for deep learning implementation due to its highly parallel architecture. And this had introduced us to second problem statement, which is demand of computational resources and storage for optimal neural network implementation. This is because people are using deep learning to work with more complicated problems, and this requires a lot of resource and storage, which exceed the limit that the current FPGA platform could offer. And lastly, it is also found that the classic method of training neural network is time-consuming and not suitable for FPGA architecture. The training of neural network itself is a time-consuming with lower rate of convergence, and then the form of weight values it gives is usually in a floating point which does not suit with the FPGA due to its storage limitation. So the existing solution available nowadays is by implementing the deep learning model in hardware platform, which is FPGA. However, in solving more complex problems which requires big neural network structure, the computational resource and also the storage issues faced by FPGA become the biggest limitation of this platform. So the method of implementation which requires low consumption of these resources is needed as an alternative to overcome this issue. In this project, we are proposing the usage of binarized parameter with the deep learning model, which means that all the values of the parameter involved in the process will only consist with value of 0 and 1. And this model with the binarized value will be trained with an evolutionary algorithm known as genetic algorithm. And why RD solution was proposed is mainly to help in reducing the resource usage on FPGA platform, as the usage of binarized parameter could reduce the amount of storage used on FPGA and simplify the operation throughout the layer of neural network. Other than that, previous work had also reported that usage of genetic algorithm is proven to be effective in finding optimal value of weight, as it also simplifies the structure of neural network as well as providing the weight value in the binarized form that can be fit on FPGA. The targeted segment for this project will be in the field of recognition, especially in the area of high-return digit, as this task itself will be specifically carried out in this project to analyze the performance of neural network model on two different platforms. And the impact of this project could give benefit to a lot of people working on industry involving recognition tasks, such as processing bank check amounts, scanning numeric entries in forms filled out by hands, and it may also contribute toward the improvement of deep learning model performance for applications such as real-time classification. And now I would like to continue my presentation for the technical part of this project. The detail of tools used in this project are divided into several categories, which is the hardware, software, and dataset. So firstly, the hardware that will be used in this project will be Intel Altera DE1 board and also VGA monitor to display the result and the image being classified. Meanwhile, for the software, Quartus Prime will be used to design and load the Verilog model onto Altera DE1 board, and Python will be used to design neural network model for the software platform. Dataset that will be used in this project will be 600 training set of 28 by 28 pixel high-return digit images obtained from MNIST database. And for the purpose of this project, these original grayscale images from MNIST will be binarized and downscaled to 8 by 8 pixel images. The flowchart in this slide illustrates the general workflow that will be covered in this project. So firstly, we start to design a CNN model for high-return digit recognition task on FPGA. And after developing this model, it will be replicated with Python for implementation on PC as in software platform. Next, the flow continue with data preprocessing and training of weight with genetic algorithm, which also being performed on PC. And then the pre-trained weight obtained from the PC will be hard-coded onto the FPGA for classification purpose. At the end of this flow, testing and analyzation of results from both of the platform will be done based on its speed and also accuracy. So for the implementation section, I would like to highlight again that both software and hardware will be implemented with similar neural network model, where CNN model will be first designed on the hardware platform, which is Altera DE1 board using Verilog code, and the model will be replicated on the software platform utilizing Python language. However, only classification tasks will be done on the hardware part, and there is no training of weights performed here. The data preprocessing of the images and training of weight with genetic algorithm will be solely done on the PC, where the optimized weight obtained later will be hard-coded in the Verilog code for classification on the FPGA. The diagram in this slide is the deep learning architecture that were implemented on both platforms, which is known as convolutional neural network or CNN. This CNN model consists of simple neural network made up from 2 convolutional layers, 2 pooling layers, and also 2 fully connected layers. The convolutional and pooling layer will work alternately to convolve and binarize the feature maps to produce 32 2x2 output feature maps, which will be flattened to 128 length of array before it was sent to the fully connected layer for classification of image to be done. So at the end of the neural network, 10 entries of array will be produced representing the probability of result for each digit from 0 to 9 corresponding to the index of array. So as being discussed before that we are going to use binarized parameter to reduce the resource usage, I would like to explain of how the binarized parameter can be utilized based on the operation involved. In this project, the binarized value of 1 and 0 are represented with 1 and -1. So in the normal convolution process that we usually use, the process involves the multiplication and addition operation, where all the value overlap between the filter and feature maps will be multiplied and added like what are illustrated in this picture of 3x3 filter. However, for the convolution process with the binarized parameter, ternary operator will be used to determine whether we are going to subtract or add the value of the feature map. In this implementation, the filter value used during the implementation is 0 and 1 instead of -1 and 1. This value can simplify the operation later to decrease the amount of DSP blocks required, as it will allow the logic of true or false to be done. So looking at this picture, when a filter value is 1, it is considered as true. So feature map will be added. Else when the value is 0, it is considered as false. So the value in the feature map will be subtracted. So at the end of this is how the calculation will occur, and the result will be equivalent with the normal convolution process. So by doing it in this way, we can have a similar result of a normal convolution process, but with a lower amount of resource of DSP block and storage used. Now I would like to explain generally of how the training with genetic algorithm can be performed. So the flowchart here shows the flow of training using genetic algorithm that was executed in the software platform with Python. The first start with generating initial population, which is the solution or weights for the image. So based on parameter, 10 solutions will be generated in the program. These 10 solutions will then be tested with all 600 test images to compute its fitness value based on the fitness function. The fitness function in this project is the ratio of the number of correctly classified samples over the total number of samples. So the higher the number of correctly classified images, the higher the fitness value of that certain solution will be. Then in the selection process, 4 out of the 10 solutions with the highest fitness value will be selected to go through the crossover and mutation to produce a new solution with the new updated value of weight. So the newly produced solution will be evaluated again its fitness, and this solution will be continuously optimized by running it through 100 generations as being initialized in the parameter. For the hardware platform, classification of FPGA is done with communication between the hard processor system or HPS. HPS will send the input signal to FPGA that was entered from the HPS terminal in Linux. FPGA will then feed one of the image based on input it received into the CNN for classification. And once the process was complete, FPGA will send back a signal for HPS to receive the output of 10 array compute. So the output was then processed and converted to probability, where the top 3 highest probability will be displayed its result on VGA monitor by HPS. So this communication between HPS and FPGA was implemented with QCs by configuring several PIO ports as input and output. In the QC setting, the signal coming from HPS to FPGA was set as output, while the signal coming from FPGA to HPS is set as input. So after replicating the structure of neural network on the software platform, few test sets were run for classification to verify the similarities of the result produced between the architecture on FPGA and PC. From result that we observe, for example as the image attached in this slide, the result of classification on both platforms produce a similar percentage of classification for image of digit 0. This indicates that the model on software was successfully replicated. However, we can observe that the computation time by FPGA was recorded at 0.004 millisecond, whereas model on PC recorded 162 millisecond. So even though that there might be an instability in measuring the time on software platform due to several factors such as existing background process and also other running program, from the result we can still conclude that the performance of speed on FPGA outperformed the model implemented on the PC, which is the software platform. Regarding the total accuracy obtained from training of weights with 600 training sites, the result achieved was 21%, and this percentage of accuracy may be lower due to the usage of binarized parameter in this project. So as genetic algorithms started with several solutions containing value of weights that were either 0 or 1, a variation of weight was hard to be achieved during the crossover and mutation phase. These inflexible changes in the value of weight caused the fitness of solution hard to be converged. So based on the graph of fitness versus number of iterations show, the fitness or accuracy of the solution stopped increasing after approximately 60 iterations. Other than that, usage of small pixel of image should also be taken into consideration, as it was found that few images lost its original form due to the downscaling process. And this is the example of the effect of downscaling for the image of digit 5. So when an image lost a lot of information, this will also introduce a lot of noise inside the data for the training process, which also affect the training accuracy. However, we still need to do the downscaling process in this project, as there is a limitation of resources in Altera the E1 board to run the convolution and recognition process with large pixel. So now let us proceed to the demonstration part of the project. For the purpose of demonstration, 7 images were initially hard-coded on both models implemented on PC and FPGA. The hard-coded image will be chosen for classification by giving an input between 1 to 7 in the terminal. The input for each image were set as in the table shown, where input 1 contains image of 0, input 2 contains image of 1, input 3 contains image of 2, and so on. And as what can be seen now, the blue screen displayed behind here is the VGA monitor that will display the result from FPGA. The terminal on the right is the software terminal to give input for the model on PC, whereas the terminal on the left is the HPS terminal that will accept input to be sent to FPGA. So for example, to do a classification for image of 0, I will enter 1 in both of the terminal. So now we can observe that both terminals give the same result for classification of image 0, and the speed recorded in FPGA is shorter with 0.004 millisecond than the one in software, which is around 143 millisecond. So for another testing, I will input 7 in both of the terminal. So now as observed, number 9 was being classified, and similar to the previous project, the speed of computation in FPGA was faster than software with around 0.004 millisecond than the software, which is 436 millisecond. So for the last testing, I will input another number, which is number 4. So based on the table, number 4 was classified and the result was as displayed. So as a conclusion, at the end of this project, similar model of deep learning were able to be implemented on both platforms, and it was also proven that neural network model on FPGA had a better performance in terms of speed than the software platform. Other than that, usage of binarized parameter did minimize the resource usage of FPGA, but the accuracy of the classification was severely affected. But there are still a lot of improvement that can be done to improve the accuracy of the model through trial and error in tuning the parameter of genetic algorithm. And the design of the neural network can also be improved if enough resources are available to add few hidden layers to the network, as well as increases the number of neurons.